It is 2:47 a.m. on a Tuesday. A merchant in Portland called Blue Barn Home receives an order. 6 dining tables, $12,400. The billing and shipping addresses both point to a luxury condo in Miami, but the IP address where the order was actually placed resolves to Ho Chi Minh City. The platform's default payment window closes in exactly 90 seconds. If this is a stolen credit card and the order goes through, the merchant eats a 5-figure chargeback and loses 6 tables. If it is a real customer and they reject it, they have insulted a very wealthy buyer. A decision has to be made right now. This chart highlights where we are in the architecture stack. Agent number 1, the autonomous decision-making agent, excels at tactical, immediate moves. But a multi-step verification process requires a wider view. Agent number 2, the planning agent, takes over. It takes the fuzzy goal of ship this order safely and decomposes it into a long arc, strategic plan with dozens of dependent steps. The planning agent treats the initial plan as a working theory. Its utility isn't found in the first draft of the task list, but in the specific ability to dynamically revise that list the instant a node fails. Surviving that 90-second payment window requires an engineering mindset that anticipates failure as the default state. The focus shifts entirely from perfect execution to perfect recovery. This diagram shows a hierarchical task network. It is the structural foundation of the planning agent's orchestrator, splitting the goal into a directed acyclic graph, or DAG, of distinct subtasks. The system uses Kahn's algorithm to topologically sort these tasks so dependencies are strictly respected. You cannot process a payment before fraud is cleared, and you cannot assess fraud before the data itself is validated. Every single node in this network carries a rigid anatomy. It requires a precondition to start, an execution policy, which might be an LLM call or a hard-coded rule, and a defined fallback state if the action fails. Back at 2:47 a.m., the Portland furniture order begins moving through the graph. The first node, basic Veda validation, passes immediately. The orchestrator moves to node 2, the fraud risk assessor. Because of the mismatched IP and the high dollar value, this node invokes a fine-tuned large language model to evaluate the complex signals. Then the primary execution path breaks. The API stalls. The 5-second limit is breached, and the LLM call times out, throwing an HTTP 503 error. This exact second, a stalled API call in the middle of a high-stakes financial transaction, is where textbook AI theory crashes into the chaotic reality of production environments. E-commerce workflows have a severe latency constraint. An LLM takes 2 to 5 seconds, but real-time decisioning demands sub-200 millisecond answers. The fix is running a lightweight random forest model concurrently. The system only escalates borderline scores to the slower LLM. When that LLM times out, the fallback state dictates the survival of the business. If the system defaults to pass, a fail-open state, the workflow shrugs and the $12,000 fraudulent order ships. This table breaks down common system risks. Look at the top row. Silent auto-approval on LLM failure is the #1 production incident. The guardrail here is deterministic. On exception, the system forces a fail-closed state, hard-coding the risk score to a maximum 1.0. That perfect 1.0 score bypasses every downstream heuristic and immediately triggers a manual human-in-the-loop review gate. The system halts. Forcing a manual review solves the auto-approval problem, but it creates a dependency deadlock. The fallback node itself can fail, because at 3 in the morning, there is no human awake to click approve. To mitigate this, the replan loop enforces a hard 15-minute timeout on the manual gate. If no human responds, the order is automatically flagged, placed in a quarantine queue, and held for morning review. Scale introduces entirely new vulnerabilities. During a massive flash sale, malicious actors will reverse engineer your specific risk thresholds. If they know everything under $200 auto-approves, they will flood you with $199 orders. When 1,000 orders a minute hit the pipeline, the human review gate becomes a fatal bottleneck. The system answers with dynamic threshold scaling. It detects the swelling queue and temporarily lowers the auto-accept ceiling for small orders, preserving throughput. Even data retrieval introduces risk. The inventory node uses a 30-second cache. If stock levels shift in the few seconds between checking the cache and processing the payment, the merchant oversells the item. The engineering solution is optimistic database locking. It ensures an atomic decrement in the database, forcing the plan to respect the inventory dependency even when the underlying data is drifting. The replan loop never rests. Every threshold lowered for throughput increases security risk. This landscape places our case study in a billion-dollar sector. While internal code is proprietary, the operational logic used by Shopify, StripeRadar, and Forder reflects this exact multi-layered risk approach. These enterprises leverage adaptive decisioning to guarantee chargebacks and secure market positions. This metric shows the macro-level efficiency of the architecture. A properly tuned workflow achieves 85% autonomous resolution. That represents the baseline volume of orders the agent processes safely, removing manual burden from the merchant and proving the system's economic viability. Their real advantage is the resilience of the directed graph in safely catching and rerouting the 15% of transactions that break. Order processing has evolved rapidly. It moved from static rule engines to basic machine learning scoring and finally arrived at full planning agent orchestration, capable of continuous adaptation. Back in Portland, the sun comes up. At 8 a.m., a human reviewer opens the quarantine queue, examines the $12,000 order, and permanently flags it as fraud. The chargeback is avoided. The planning agent performs its final action. It takes that manual adjudication log and hands it directly to agent number 3, the memory-augmented agent, for persistent cross-project learning. Fraud vectors change seasonally. To combat this concept drift, the LLM's knowledge base is updated daily with new chargeback reports, and the risk model is fine-tuned weekly. The system gets smarter every time it fails. This human-in-the-loop fallback is transitioning from an engineering best practice to a strict legal requirement. Regulators are moving aggressively on AI fairness and automated decisioning. With directives like PSD3 taking effect in Europe, these deterministic guardrails and required manual safety gates will become the legal standard for all automated financial systems. Safely failed closed to a human gate and learned from the final outcome. The merchant woke up to a handled situation. No lost inventory, no frantic midnight calls. That is the quiet power of bounded autonomy. The agent runs the long arc, but knows exactly where to stop. The architectures and patterns driving these replan loops are detailed extensively in Imran Ahmad's 30 Agents Every AI Engineer Must Build. In our next episode, agent number 3, the memory-augmented agent, picks up exactly where tonight's log file ends. Check the links below to study the documentation and keep building.